Hi guys. Here's a practice problem for Gauss's law. We're going to have a quiz next class, and in this situation we've got a point charge at the origin, little r equals 0. We've got a metal shell, inner radius r and outer radius twice big R, and we have a plastic shell. Now the plastic shell has charges, but those charges are uniformly distributed throughout the volume. Just a reminder, Gauss's law, if you've listened to my intro video, that's great. If you haven't, you might want to listen to it. Gauss's law in the spherical case reduces down to determining the electric field, the radial component of the electric field. It all comes down to just determining the amount of charge inside of a distance little r from the center of the distribution. So here, this is a typical example of what the quiz will look like next class. And always start on the inner region and work your way out. I've labeled the regions 1 through 5. The regions 1, 3, and 5 and 4 will all have fields. Let me start with sort of the easy one. There is a field in 2 also, but that field is 0, so there is no field inside of metal in equilibrium. So region 2, so I'm just going to start with that. It's really the easiest thing to talk about. So region 2, which is little r greater than r and less than twice r, you just say little r equals 0, er equals 0, because you're inside of metal in equilibrium. Now region 1, which is for little r between the origin 0 and little r equals big R, in that region, Qn is just the charge at the origin, which is given that that's the point charge Q. So Qn is just Q in that region. So the electric field, the radial component, just goes like kq over r squared. So let's actually plot that right away. Just do that. It goes up asymptotically with the vertical axis there. And the value at little r equals big R is going to just be kq over big R squared, like that. So very simple. Now before I start talking about determining the amount of charge on the inner and the outer surfaces of the metal shell, let's determine the field in regions 3 and 5, because that's relatively easy. So region 3, what do we have? Well, region 3 runs from sorry about that, runs from twice r to 3 times r, big R that is, and Qn is equal to that point charge at the origin, little r equals 0, plus the net charge of the metal shell, and it's given that the metal shell has a net charge of Q, right? So that means Q plus Q, metal shell. So the total charge inside of a dude, a Gaussian dude, who is in region 3 there, is going to just be twice Q. And therefore, the electric field will be twice kq over little r squared. That's our function of little r. Let's plot that too while we're at it. So at twice big R, here goes, little r equals twice big R, you're going to have 2kq over twice big R all squared, and that's going to give you 1/2 kq over twice big R squared. At the outer extreme of that region, little r equals 3r, you're going to have, you can do it in your head, 2/9 kq, ooh, that's a q, over a big R squared, like that. So that's easy enough. 1/4 would be half what it was before inside of the metal shell, and then it goes down to something almost about half that. So I'm going to put here, that'll be 1/2 kq over r squared. The other one, I'm just going to write it up here. Right? I'm going to write 1/9, because there's no room on the vertical axis there. big R squared. Still positive. Okay. And that's going to fall off like that, right? Now the outer region, region 5, let's go for that because that's still relatively easy. The outer region, region 5, what's the net charge of our uniformly charged plastic shell? It has a total net charge of negative 2q. By the way, this is the plastic shell here. I'll just label it so you guys can see it a little bit easier. So, starting from the center, so we're in region 5 now, which is just little r greater than 4 times bigger R. And adding up from the origin out all of these charges, you've got the Q at the origin, you've got another Q, which is the metal shell, and then, of course, the other shell, which is the plastic shell, which is a net charge of negative 2q. So altogether, interesting, it's a 0, right? So that means the field out there is 0 as well. So no field out there. So we've only got 2 things left to do, right? We have to determine how much charge is on the inner and outer surfaces of our metal shell, and we have to determine the functional form of the field inside of the plastic shell. So let's start with a more familiar thing, which is determining the charges on the inside and the outside. By the way, that's problem C and D. So I'm going to do that here where I have some room. Because there's negative 2q there, I know the field is just going to decrease to 0. So in the plastic shell, the details of how it happens, we're going to work that out in a moment. But I know I'm not going to go negative, so I'm going to use this space below the graph here to actually work out C and D. Okay, well, if you listen to my previous video, you'll know that to make the field 0 inside of a metal shell, what you have to do is you have to put on the inside surface, so I'll call this the charge at little r equals big R, you have to put a charge that's equal and opposite to the charge inside of that point, and the only charge inside of that point is R plus Q, go away, R plus Q at the origin. So you absolutely have to have minus Q on the inner surface. Now the net charge of this thing is given as Q, and the net charge is equal to the charge we just talked about on the inner surface plus the charge on the outer surface at little r equals twice big R. And because we know this is negative Q, that means the only thing that can be, because they have to add up to Q, has to be what? That's right. It's got to be twice big Q, right? So we've determined them. We know what they are. And this is my reasoning right here. This is so that I'll just put that in parentheses there. ER equals 0 in metal. That's the really important step. And then it's just what's the net charge and determining the amount of charge on the outer surface. So the only thing we have left to do is determine how ER varies inside of the plastic shell. And we got this space down at the bottom. So we're talking about region 4. Region 4 is this cross-hatched region up here. And if you go through our notes, our class notes, you'll see that what it comes down to, since it's a uniformly charged shell, here I'll draw a little bit, you need to work out the volumes of the entire shell and the volume of the region that I'm not going to go all the way around, but that shaded red region right there, right? And the argument goes like this. What we need, change color here. I'll do it in green. What we need here is to determine how much charge is inside of the plastic. There's the total amount of charge in the plastic, but this is the amount that's inside of, let me be very specific here, little r, right? That's where the Gaussian dude is, and we're trying to figure out that amount of charge that I'm calling Q in plastic, that's in this red region here, right? So it's proportional to the volume So I'll just call that Vn. And this is the total volume of the plastic, like that. And if you go back to the notes, to calculate the volume of a spherical shell, you need to calculate, it comes down to the outer, especially a ratio like this. I'll write down everything. The green doesn't show up very well. I'll go back to black. The total volume, let me start with the denominator here. Whoa. Sorry about that. That is annoying. The total volume of the plastic is going to be equal to 4 pi over 3 times the outer radius of the plastic. I've forgotten what it is. It's 4r, right? 4 big R cubed, minus the same thing. You remove that inner volume and you create a shell. So that would be a solid, this thing would be a solid sphere. And by removing that inner thing, you create a shell, basically, cube. And then in the numerator, we have the volume of that red region that I partially drew up in the picture there. And this is going to be, now the outer radius is no longer 4r, it's our Gaussian radius. So you put that cube. These 4 pi's over 3 are all going to cancel, so don't worry about that too much. And then it's, again, you remove the inner volume to make a shell. And there we go. So the 4 pi over 3's are all gone. They all cancel because we're doing this ratio argument. What is Q plastic? Q plastic is actually, is it negative 2Q? Yeah, negative 2Q, right? So this is going to be equal to what we want to know, which I'll call Q in P for plastic. And this is negative 2Q. So we're going to solve for that. You can expand these things if you want to, but if this were a test, I wouldn't even bother, right? I would just go like this. This would be negative 2Q. Oh gosh, I can do it in my head. R cubed, in the numerator there, 3 cubed is 27, so that'd be 27, big R cubed. And then downstairs, cubed, 4 cubed is 16, 64 minus 27 is 37. So downstairs doesn't really matter, you know, I don't really care because we can't plot this thing anyways, right? So the big thing that you need to know is the total amount of charge inside of that point that we're at, which is a distance little r from the center somewhere in the plastic shell. You're going to have that charge at the origin plus the net charge of the metal shell, right, plus this. And I'm just going to write it like that, right? And then, of course, once again, ER as a function of R in the shell is just going to be this thing divided by R squared. And we can't plot it, and we're done, right? So this is region, well, I didn't label that. This is region 4. Let me make that nice and clear. And that's enough, right? And you just go, see below. And we're done, right? We have plotted out the field in all 5 regions. We have looked at, we've determined what it is at the endpoints of the regions, right? At little r equals big R, twice big R, and 3R. And we have determined in C and D here, this is essentially C and D. I guess that's C, and this would be D right there, like that, right? We have determined how much charge is on the inner and the outer surfaces of the metal shell. So that's it. That's going to be more or less similar to the quiz that I will give you next class. Okay, I hope this helps. I'll see you in class.